function is a rule that describes how one quantity depends on another. Many real-world situations follow precise rules so they can be modeled by functions. For example, there's a rule that relates the distance a skydiver falls to the time he or she has been falling. So the distance traveled by the skydiver is a function of time. Knowing this function model allows skydivers to determine when to open their parachute. They don't want to open it too soon. They also don't want to open it too late. In this chapter, we study functions and their graphs, as well as many real-world applications of functions. All right, so functions are all around us. In nearly every physical phenomenon we observe, that one quantity depends on another. For example, your height depends on your age. And your height depends on your age, but kind of within a parameter, right? You grow only for so long, right? And then after that, your height may stay very, very constant, or it might even decrease. Right? So the rule that describes your height when you're younger may not be the same rule that describes your height when you're older. But here we have on the right here we have an example. All right, so maybe the person grew between 20 and 25, and that would, for a male, that's possible. For a female, that's not. All right, but after that, height will stay constant, and it might even go down a little bit. Temperature is a function of date. Right? Some areas have temperature where it's very constant. Right? Other places, right? If it's winter time, the temperatures are much colder. Right? Already here it's much colder, but our temperature kind of zigzags a lot, like this one does. So just because a date is later than the current date doesn't mean it's necessarily going to be colder. Cost of mailing a package is a function of weight. This one is very specific, so we don't see a lot of change in that one, right? So this one happens to be in 2014 dollars. So if it's between 0 and 1 ounce, you pay a certain amount. And then notice you don't pay as much for each additional ounce, but you do pay more. Right? Some of these functions have different rules for different parts of the function, right? And we're going to learn about functions that have different rules for different parts of the function, and that's called a piecewise function. So, by the way, the last one, I didn't read the little caption here, but the U.S. Post Office uses a simple rule to determine the cost of mailing a first-class parcel on the basis of its weight, but it's not so easy to describe the rule that relates height to age or temperature to date, right? Just because a date's later doesn't mean it's in the year, it doesn't mean it's colder, and just because you're getting older doesn't mean you're getting taller. Can you think of some other functions? Here are some more examples. The area of a circle is a function of its radius. The number of bacteria in a culture is a function of time. The weight of an astronaut is a function of her elevation. The price of a commodity is a function of the demand for the commodity. Some of these are easier to write equations of than others. This one and this one is really easy to write an equation of. In the first case, the area of a circle is a function of the radius squared. All right, so that's an easy one to write an equation for. The second one we can easily write an equation if we know the rate of change. All right, so if we know how the bacteria are changing. This second one is an exponential function. We won't really be working exponential functions in this particular lesson very much, but we will in a future lesson. All right, so here, we'll just call it B for bacteria. The bacteria, all right, so A is our starting amount, and I don't know how many bacteria we're starting with. And then we're going to have a base, and this is going to be a number. If it's continuous, if you remember from last year, it would be E. If it's not continuous, right, if it's doubling or tripling, that's what our B is going to be, and that's going to be raised to a power. Right? So that's what it'll look like for the number of bacteria. Whoops, I shouldn't use the same letter. Sorry. Let's not use B. Let's just call it something else. I forgot I already used B. So bacteria is equal to the A is the starting amount, and let's call it R for the rate of change. Right? And that's going to be a function of time. Right? Because bacterial growth is an exponential function. But the other two may not be as easy to write an equation for, unless we already know an equation for those. So definition of a function. A function is a rule. To talk about a function, we need to give it a name. We use letters such as F, G, H to represent functions. For example, we can use the letter F to represent a rule as follows. F is the rule, square the number. All right, so when we write f of 2, that means we're applying the rule f to the number 2. Applying the rule gives f of 2 equal to 2 squared, or 4. Similarly, f of 3 would be 3 squared, or 9, and f of 4 would be 4 squared, or 16. And in general, the equation that represents that rule is f of x equals x squared. Right? And once I've defined a function, once I've said that f of x equals x squared, I can just call that function f of x. So definition of a function f is a rule that assigns to each element x in a set A exactly one element called f of x in a set B. So in other words, every element in your input is matched to one and only one element in your output. We usually consider functions for which sets A and B are sets of real numbers. Right? So we are going to be working with real numbers here. The symbol f of x is read, just the way I read it, f of x. I don't hear it much f of at x, but it can be said that way. And it's called the value of f at x, or the image of x under f. The set A is called the domain of the function. So the domain is the same as your input. So you do have that diagram. So next to input, you can put domain. The range of f is the set of all possible values of f of x as x varies throughout the domain. That is, the range of f is equal to f of x, where x is in this. So this is what this means. This e here, this funny looking e, means is an element. So in other words, we plug in elements of our input into the rule for the function, and we get an output. That output is the range. It's our y. It's typically our y values. Right? Usually y is going to be our variable for our output, and x is going to be our variable for the input. The symbol that represents an arbitrary number in the domain of a function f is called an independent variable. So x, which is the input, or our domain, is the independent variable. The symbol that represents a number in the range of f is called a dependent variable. So f of x, which is our output, which is our range, is the dependent variable. So y depends on what we plug in for x. It's helpful to think of a function as a machine. If f is in the domain of the function f, then when x enters the machine, it is accepted as an input, and a machine produces an output according to the rule for the function. Thus, we can think of the domain as the set of all possible inputs, and the range as the set of all possible outputs. And we can have an infinite number of inputs and an infinite number of outputs. And some of our functions do have an infinite number of inputs and an infinite number of outputs. Another way to picture a function is by an arrow diagram. That's helpful if you have a finite set, not as helpful with an infinite set. Each arrow associates an input from A to a corresponding output in B. All right, so here we have a finite number of inputs and outputs. All right, so we can represent it with an arrow diagram. A is the input, right? And when we plug, so for instance, when we plug in 1, we get 20. If we plug in 2, we get 20. We plug in 3, we get 30. We plug in 4, we get 40 in example A. In example B, we plug in 1, we get 10. We plug in 2, well, maybe we get 20 and maybe we get 30. Who knows? We plug in 3, we get 40. We plug in 4, we get 50. So because in the second example, we don't know where to go when we plug in 2, that is not a function. So for a rule to be a function, each arrow associates an input with one and only one corresponding output. If any input is associated with more than one output, then that particular mapping is not a function. So B there is not a function because 2 is matched to 2 different outputs. It doesn't matter if so notice in A, we've got 1 and 2 both matched to 20. That's okay. You can have 2 inputs matched to the same output, right? Think of a parabola, right? Whether I square 3 or whether I square -3, we'll still get 9. That's okay. I know if I plug in 3, I know where to go, 9. If I plug in -3, I know where to go, 9. And if in our example below here, if I plug in 1, I know where to go, 20. If I plug in 2, I know where to go, 20. In the second example, if I plug in 2, I don't know where to go. It's either 20 or 30. All right, so B is not a function, but A is. Analyzing a function. A function f is defined by the formula f of x equals x squared plus 4. All right, so we're going to do A, B, C, and D, and this one is in your notes. A, express in words how f acts on the input to produce the output. I'm going to write the answers below because I did not leave myself enough space, nor did I leave you enough space. All right, so what do? We have x squared. All right, so we square the input, and then we have plus 4. And then add 4. Notice we have to square first, then we add 4. Evaluate f of 3, f of -2, and f of the square root of 5. And that just means that we are going to plug in 3 and -2 and square root of 5 for x. That's our input. That's the variable for the input. So f of 3 would equal 3 squared plus 4. So that's going to be 9 plus 4, or 13. F of -2 equals, now here it's important I use parentheses because I have to remember to square the negative. All of x is squared. That means all of whatever I plug in is squared. So -2 squared is 4, and 4 plus 4 is 8. And then f of the square root of 5. So I have the square root of 5 squared. By the way, the parentheses here is optional, but sometimes if I have a square root and then I have it raised to a power, sometimes it looks too much like, in this case, 52 instead of square root of 5 squared. So that just makes it look clear. Square root of 5 squared would be a square, and square root will cancel, right? So we have 5 plus 4 equals 9. All right? And now that's all there is to evaluating, is substituting whatever value we have for x and then applying the rule. Find the domain of and range of f. All right, so now the domain, this is a quadratic equation. There's no number, there are no domain restrictions on what you square. You can square anything you want, right? We could square negatives, we can square positives, we can square roots, right? We could even square imaginary numbers if we wanted. However, we are going to limit our domain to just the real numbers. So our domain is -infinity to infinity. Our range, however, is restricted. And I'm just going to do a little sketch over here. All right, so we have a parabola, and I'll just do a small sketch. All right, so if I plug in, so if I just look at this part, the f of x equals x squared, this is a parent function, right? And f of x equals x squared, if I square 0, I get 0. If I square 1 or negative 1, I get 1. If I square 2 or negative 2, I get 4. So this is the equation y equals x squared. The equation we have is y equals x squared plus 4. That parabola has been shifted up 1, 2, 3, 4. And so I didn't graph enough, but so now our parabola is up here. So if you remember from last year, we transformed parent graphs, right? And so that f of x equals x squared plus 4 is just a plain old parabola shifted up 4, right? So our vertex now is located at 0, 4, right? So when we have a parabola, right, it turns around at the vertex. So that means our range, I should specify what the negative infinity to infinity was. That's our domain. And the range, I'm going to move D. D is not going to fit there. The range is going to be 4 to infinity. We use a bracket because our function does go through the value 4. All right, so now draw a machine diagram for f. All right, so now here's what our machine diagrams look like. Oops, too far. All right, so there's our machine diagram. All right, we're essentially going to draw that, except we're going to change what f is. So I don't know how well mine is going to look, but all right, so we have our input, which is x, and just call that the machine. Good enough machine. All right, so here we have x rule, which is f of x equals x squared plus 4. All right, and then our output are the values we get for f of x. All right, so there's our essential machine diagram. Our rule is x squared plus 4. We're going to square all the numbers and add 4 to them. And we can do that for an infinite number of numbers, but I think we're going to stop. Evaluating a function. We'll do this section in this video, and then I'll pause to do the next video. In the definition of a function, the independent variable x plays the role of a placeholder. For example, the function f of x equals 3x squared plus x minus 5 can be thought of as, so everywhere we see an x, we're going to substitute some value, and we're going to substitute the same value for every place we see the x. All right, so here we're going to evaluate this function, let f of x equal 3x squared plus x minus 5. Evaluate each function value. All right, so A, and this one's also in your notes, f of negative 2 means we have 3 times negative 2 squared plus negative 2 minus 5. So that would be 3 times 4. Now actually, if you're okay, let's just write, we can do 3 times 4 in our head. That's going to be 12. And this is just 12 minus 2 minus 5. And so that would be 12 minus 2 is 10 minus 5 is 5. B, f of 0 equals 3 times 0 squared plus 0 minus 5. Well, I'm going to have 0 plus 0 minus 5. And so that's just going to be negative 5. F of 4 would be 3 times 4 squared plus 4 minus 5. 4 squared is 16 times 3 is 48. 48 plus 4 is 52. Minus 5 is 47. And then the last one, f of 1/2 equals 3 times 1/2 squared plus 1/2 minus 5. We're going to have to get some common denominators here. 1/2 squared is 1/4. Right, you square the 1, you square the 2. 3 times 1/4 is 3/4. 1/2 is the same as 2/4. And 5 is the same as 20/4, right? Because 5 times 4 is 20. So that's going to give us 3/4 plus 2/4, that's 5/4. Minus 20/4 will be negative 15/4. All right? And I'm going to pause here, and then I'll see you in the next video. Bye for now.